Hi, when we're programming in a high-level language like App Inventor or JavaScript, we don't need to know very much about what goes on in the hardware of our computer. However, in order to understand how the Spectre and Meltdown exploits work, we do need to have a pretty good technical understanding of what's going on inside the system, and in particular at the processor level. What I've done here is to create a system diagram, basically a block diagram, illustrating some of the major components of a computer. This isn't necessarily meant to be accurate, it's meant to be a simplified drawing of a computer. Some of the things we have here, of course, are the processor or CPU. When you hear that your computer has an Intel or AMD processor inside, this is what we're referring to, the CPU. CPU stands for Central Processing Unit. Some of the other major components that we have in our computer are going to be the RAM memory. If we have an Android device, we would also have flash memory. We're also going to have some way of displaying information onto a video display or an LCD display. We're also going to have several types of interfaces on the system. The universal serial bus may be used to connect to a mouse or keyboard or even another hard drive. We also have a PCI Express bus that can be used to create additional functionality with add-in boards. Connecting this together, we have something we call a system bus. So we'll kind of look at this area right here. The system bus is actually an interconnection of carrying signals between the central processing unit and the various hardware components of the computer system. When our computer is running, it's actually pulling the program instructions out of RAM memory. And the exception to that would be an Android device that may be pulling instructions out of flash memory that I haven't shown here. So we'll just kind of put this here, just so we know that flash memory can also exist. Now, what we're actually talking about, though, is a typical PC type device. We probably copied our program when it's running from the hard drive into RAM memory. We take instructions, are read out of RAM memory, and put into the central processing unit, where they are decoded and then executed. What that means is let's say we had an instruction that looks like something like this. That might mean take the value of R1 and add it into R2. So that's a simple machine instruction, and this is a topic that we will discuss in a later video so you can see how this all relates. When the program is running, we're going to take that instruction, it's going to go into our CPU, that's called the fetch portion of the execution cycle. We're going to decode it to decide what it is we need to do. We need to add some numbers together, and then we're going to execute that. Here we're going to actually do this function. And it may be that another instruction maybe says something like move to a memory address the value in a register like R3, in which case now as part of that operation we need to take some value and put it back into memory. So this is a very simplified drawing of what's going on inside your computer. Software programs are running, they're also sending signals to and from video, they're reading data from hard drives, they're interfacing with your keyboard and mouse and any other devices on the USB port. Now we'll drill down a little bit into the CPU itself. It's got another drawing over here that we'll take a look at. This represents the processor, and we talked about how we're reading instructions out of RAM and they're coming up here through the system bus into the processor. When it reads the instruction, the first thing it does is it has fetched it from memory. Then it decodes the instruction to decide what it is we're going to do next. Then it actually executes the instruction. Some of the components that we'll find inside here are things like the arithmetic and logic unit, or ALU, and there may be several ALUs, and commonly are several ALUs inside a modern CPU, so that the computer can do multiple arithmetic operations simultaneously. So again, when we write an instruction like add R1, R2, that actual addition is going to be performed by the ALU. There may be other components inside that processor as well. We also have a set of registers. We've actually seen these already when I wrote R1 and R2. Registers are places in memory inside the processor that it can access at absolutely top speed. There's no wait time to gain access to those. The number of registers that may be present could be 16 or 32. It all depends upon the nature of the processor design. Some other registers, the instruction pointer. The instruction pointer keeps track of where the next machine instruction is located. So let's say, we'll just make this up here. We'll say we have a memory address of 100. Obviously, we typically have addresses that are really big, but we'll have here something like move R1, and we'll say the value 3. And we're going to do this sort of backwards this time. There's different ways of writing the notation for this type of machine instruction. I'm saying here that we're going to move the value 3 into the register R1. Other people might reverse that and say it's 3 comma R1. Different processors do it differently. Different languages do it a little differently as well. Now we're going to have this other instruction. We're going to pretend now that the add instruction is over here. And so at this point, our instruction pointer is actually pointing to the next instruction to execute. Once that has completed, we move on to the next instruction in sequence, and so on as we continue to run the program. Another register here is called the stack pointer. We're not going to get into the stack or the stack pointer and how that operates, at least as part of these videos. The register file we've already covered. We haven't talked about the cache memory down here. And where does this fit into the scheme of things with RAM? Well, let's say we had an instruction here that was going to be something like, shall we say, move, let's say, the value at memory location 1000. And what we want to do is, I'm going to squeeze this in here, we want to move the value at memory location 1000 into register R1. So after it has gone through the fetch, decode, and now the execute step here, the CPU has to go out and say, find me the value of whatever is stored at 1000 in memory. And let's say we have a value in 1000. We'll say it has the value 99. I'm just making these numbers up as we go along, so these aren't important. The first time it encounters this reference to the address 1000, it has to say, well, go fetch it. And it goes down here to the memory and says, return the value at location 1000. This is actually a very time-consuming step in a processor. The processor runs much, much faster than your general system memory. So this means it has to wait while it's reading that value in. Once the value becomes available, it can go back into the processor and the processor could continue execution. Now, obviously, we'd like to speed that up. One of the ways that we can speed that up is by having some other types of memories that are actually built into the processor. These are known as level 1 and level 2 cache memory. These are very fast memory that is much faster than RAM. So you might ask, well, why don't we just put all fast memory everywhere on the computer? Well, the reason is usually due to cost. It's simply much more expensive to make very fast memory like this than to make good memory down here that's not quite as fast. So we just don't do that. Instead, though, we'll create a cache memory where we'll keep values temporarily that are used frequently. So the first time through, we fetch the contents of 1000, and we're actually going to make a note that we have the value of 1000 and the value of 99 stored in that cache memory. The next time our program is running through and it encounters this, let's get the value of 1000 and do something with it, it's going to ask the cache memory, hey, do we have the value for 1000? If yes, we're going to return that value to the processor really fast and not have a long wait time. Now, because we mentioned there's only so much space we have for that expensive memory, so we actually do layers of this, and there's typically an L2 cache of maybe 256 kbytes. So that's another set of memory, and these will trade back and forth with their memory as they go through here. We also have some other concerns to make, which is, well, what about when this gets full? Well, obviously when it gets full, then we have to remove some of the stored values from here. If we have updated those values, say change their value to it's no longer 99 but 100, then what we have to do is we have to flush those values back out to RAM. So these are going to get written back down here. Now, this is important to understand because how the cache memory operates is actually central to how the exploits like Spectre work. So we want to have just a little bit of an understanding of what's going on there. I'll also mention here that there is also something called a level 3 cache. And we'll typically see that when we have more than one central processing unit, like a dual core processor. So let's draw this out here. And they'll have each their internal L1, L2 inside their CPU, but they may have a shared cache between the processors because they might both be working on the same problems and have data in common with one another. So that's another level of cache memory that may appear in our system. What we'll look at in a subsequent video, we'll take a look at these machine instructions so we can see a little bit more about how this works. We'll also learn how, surprisingly, the instructions in our programs are not always run in the order that we have written them in. And that's due to a couple of things. One is called speculative execution. We mentioned that sometimes the computer has to wait to get values from memory, so sometimes the processor will guess at those values. That sounds crazy, but there's ways of trying to make good guesses so that it can continue processing without waiting. If it guesses wrong, then it has to back up and start over again with the correct value once that value has come out of the RAM memory. Another example is something called out-of-order execution. And that's because sometimes it doesn't actually matter exactly what order the instructions in our program are executed in. And there may be reasons for the processor to change that order in order to optimize the total use of the processor, especially when you think about having multiple threads of execution running through a computer at the same time. These are topics for a future video. My next video will start to talk a little bit about how our computer languages work to get translated into these kinds of instructions. And once we understand that, then we'll come back and look more at how the CPU works and how the Spectre exploit works.